Okay, well, I guess everybody's asleep, but I should press on with this. This is kind of review stuff. And this bit too is a little bit on the review side. Things you should know. I have my parametric functions working. This is one here. Now, this is going to change, but as it is now, deriving from this thing. And I can't help it, I gotta make this visible to the derived classes so because of what I plan to do with this parametric function class. What I want to do is put essentially everything in the one class instead of deriving from it. This class will take objects of this type in its constructor so that one can manipulate the function. Anyway, just to show you what I've got here. This here is an y of x type function. These are some dots I added. Okay, so they're not drawn with lines. This here is also a y of x type function. And these two things are parametric functions of type vector. And the way a vector works is either 2 points, and to calculate the position as a function of t, you take this here is meant to be a vector in that it has direction and magnitude. So these are the 2 points, the endpoints of the vector. So we want to go from point 1 to point 2 over some interval, and that interval I decide is going to be from 0 to 1. So when t equals 0, we will be at point 1, and when t is equal to 1, we will be at point 2. Point 1 plus point 2 minus point 1 gives point 2. So that's what that vector is. And this one here, just to demonstrate the idea of a vector, is a vector created with the same parameters as this one, but I've added an offset, an equal offset to both points. So as you would expect, it's not starting from the origin, but it's in the same direction and has the same length. It might not look like it's the same length, but they in fact are the same length. It's a bit of an optical illusion, I think. Now, I really only want to deal with these parametric functions. And what I'd like to point out is, well, firstly, how one can describe just a straight line in terms of vectors and a parameter, that is, in a parametric form. Okay. Now, the way to do that, typically, is to start with some point on the line. Now, I happen to know this sloped line has these 2 points. Minus 50, 50 is one of them. Minus 50 and 50, that's here. Right? should be on the line. Anyway, it looks like it's on the line. And we take a vector from the origin and draw a line to that point, 50-50. It could be any point on the line, but we choose that one. And then what we need is a vector, preferably a unit vector, in the direction of the line. And the parametric form for a straight line becomes, maybe I should keep this available, I can get to the help. Is the following. Suppose P0. Now I want to find out about that bar thing. Hang on a second. Where's the hell? Frac, squirt, functions, L arrow. Oh yeah, okay. 2, that's good. Imply. But I want those up and down things. I can go through here. Sometimes works. I just want to be able to draw a vector arrow. Okay. What I want would be in which category? Here maybe. Yeah, this sort of thing. Vec. Look up vec. Okay, what I really want is that. Right? Suppose that vector is on the line, and that the line is parallel to another vector, which we'll call just V, maybe. Vector vec. V. All right. Then the AA parametric form for that straight line, and there's only one according to the Greeks, is the following. T, what was the arrow? 2. Okay, go away. How do I get rid of this thing? How do I get rid of it? How did I get rid of it last time? Oh, great. I lost the thing I was typing. Maybe in my drafts. Okay. T2 at any point P on the line okay it's given by maybe I should just add to that equals no the inside come on there we go T naught plus T dot there we go all right for T from essentially from any values of T. Now how do we do that? T element and logic. For all T, where's the element of? That's like sets, but this is really the element of. What does this say? Okay, for all T, for T and doesn't look right. It should be this. Maybe in R. Something like that. I want to make it pretty. Okay, so for all values of T, each value of T returns to you a point on that line, and in particular, if T is equal to 0, you get the point that you already know is on the line, and as you increase or decrease T, the point moves along the line. So we should be able to do that with our line. Turn it into a parametric form. So first I want to draw a vector to a known point on this. Actually, let me move this further away. I'm going to move it out higher. A little bit higher. Let's try and see what this looks like. Just so it's clearer. And then I want to adjust T and draw a point along. Watch the point move along the line. Now the difficult thing about working with these parametric forms is deciding, okay, it's not too bad. So we can choose this position. So I'm going to make a vector from the origin to here. Forget about this one for a minute. And I'll just draw it. And then what we need is a vector, and as I said, preferably a unit vector, and there's a definite reason for that, in the direction that has the same slope as the line. Now, to create a vector that's in the same direction as that line is quite easy. So here's the first vector, okay, v1, or p, that's our p0 here, right? So if we made a parametric form of this thing, this point would correspond with t equals 0. We're taking that as p0. Okay. Now what we need is a vector in the direction of that line. That's easy to make. Now I'll make one. Create. All we need to do is take any 2 points on the line. Well, here are 2, right? 2 of those points. And that will be a vector in the direction of the line. Whether it's positive or negative, it doesn't matter. What color should we make it? We'll make it blue. We'll add that. Add that to our graph. And we should get rid of the noise. We want this, we want that. We don't need the sine function. And we don't need the dots. All this is going to show that I'm going to draw. This is going to be drawn, and it's actually going to be lying along the line. It doesn't have to be. If it's really a vector can, only has direction and magnitude. Doesn't have, so there it is. Doesn't have position. Okay, so here's a vector that is parallel to the line, and here it's a vector which when centered at, or starting at the origin leads to a point on the line. So if we take this position and add some multiple of, just a floating point number times this, that just makes this vector grow, right? We will cover all the points along the line. Now this is great and everything, except first, it's too big. It would be good if we could make this into a unit vector so that we can make a parametric form. We can make a parametric form for this line. We can get rid of this. Okay, I can make a line. Line. That consists of two things, as I just showed you. Point P0 if you want, and then something that is parallel to the line. We call it V. Okay, P and V, right? Parametric line star create taking two vectors. Right? Now to create the line, we need a constructor which takes those two values and just set these equal. We can set right now and just set them equal, but in the end it would be better and will be if we modify this V so that its length is 1. Because now the difficult bit is how to determine what the range is. Right? These parametric functions have a range, I decided, of values of t for which the function would be defined. It could be infinite, but that's not very helpful for someone who's trying to draw it. But we could take it as given, the minimum and max values of x and y that we know. But really, what should we put for the minimum and maximum? Okay, well we know the function pos, right? Be public, doesn't have to be public. Pos. That's going to be this thing plus t times this thing. That's how you get any point on the line. The question is, what's a good range for these for this t, so that it's something reasonable for someone to use. Now, t times vector. Well, if we could turn this into it's not hard to turn one of these vectors into a unit vector, right? Let's see if we can do that. I have a function for determining the magnitude of one of these d points. Mag. So let's not put this in yet. Okay, that actually is called dist. This takes a point, and it will take it takes 2 points, but although to get the magnitude of a particular thing, it just takes 0 for one of the points, and this is just the root of the sum of the squares. You know, what I would like to do then is to make this into a unit vector. All I gotta do is multiply that by 1 over this magnitude. Okay, so now this is a unit vector. And so what that means is that if we change t by an amount 5, let's say, then that would move the point along the line exactly 5 pixels worth of distance. So that's the advantage of having this being a unit vector, and also of the parametric form, is that if you want something to move at a constant rate along a slope or something, a known rate of speed, then that's quite easy. You just let this t increase at exactly the speed that you want that thing to move, right? That would be quite difficult computation if you had only the y of x form of the straight line, because increasing x, just these, if you have f of x and you increase or decrease x at a particular rate, then depending on the slope of the line, it's going to move faster or slower. This here doesn't depend on the slope of the line. It's going to move at the same speed regardless of the slope. So now we can sort of guess what minimum and maximum might be. We can just take a wild guess, and let's say we saw that line. We're not using this yet. Okay, will it compile? Just take a guess as to the length of that line, and then we can fiddle around with the numbers. It's probably about 1 or 200. Cannot instantiate. Oh, const. Sorry. Both of these should be const. I'm not even using it. Shouldn't care. It'll get there. Currently it's going to display it as it had previously. Just look at it and take a wild guess as to the distance, and then we'll let t run back and forth through that distance approximately. The way that these functions are drawn is it computes. Okay. I'd say that from here to here, we can figure out exactly, but it's certainly more than 600. Let's say, just 700 or something. So minus 350 to plus 350. Now the way that this thing draws a parametric line is by taking a guess. I can improve on that guess, but parametric function, what it does is it computes the position of at the minimum value and the position of the maximum value, gets the approximate length by taking the distance between those two, and then the number of points it's going to draw is that distance divided by 30, and no fewer than 2. It has to be at least 2 points to do a line to. Okay, so now let's see if it works. P line parametric line create. Now we can use the this takes 2 points. We need 1 point on the line and something parallel to it. Well, we have such a thing. That's this line. This difference. This minus this. Or this. No, is it this one? No. This minus. It's the one we had previous. This difference is a vector parallel to the line, which will be turned into a unit vector, sign not being taken into account. We can make it yellow again. Well, I don't know if this is going to work. So we have a parallel vector and we have a point on the line. Let's just see if it, well, supposed to turn this. Just see if it comes out sort of right. I thought I had a magnitude. I could use magnitude. This uses mag, right? Mag is a special optimized function for computing the magnitude of a double or float. It turns out that taking the sum of the squares and then taking the square root of that is not good if one of those numbers happens, if either of the numbers happens to be quite large. You lose a lot of accuracy. But if you do that trick there, you don't lose the accuracy. Okay, so here's this vector, great big vector, whose length is 114. So here now that should be a unit vector. We can see if that's true. Can I copy these? Come on. Copy. No. Copy. No. I might need to. Okay, 0.876. Plus 0.482 square root well, that looks like 1 to me. It was 1 already. Okay, so this is definitely a unit vector type thing. And we've guessed that these might be this might be the range. So now, it's not drawing it. We want to stop in here. So yeah. Okay. Now is that our line? Oh no. Min 3. Okay, that's the one. Point min. No, that can't be right. No, there's something wrong here. Pause. 0.0. Did we set that? Yeah, T is 350. Let's make sure that it comes into here. Okay. Great big number. Let's see where this comes to this point. Okay. Point P. Oh dear. This is supposed to be V. Okay, that explains that. This should be an underestimate. You should see most of the line, and it wouldn't be out of bounds. But you see how easy it is? Just 1 point plus some constant times a direction. That's how you draw a straight line in parametric form. That's true in 2 or 3 or 12 dimensions, it doesn't matter. Okay. Oh. Minus 256, that sounds good. 350, that's, yeah, they seem right. Number of points 23, at intervals of 31 point something. And there it is, it went off too much. So our max is too high. Say 300. Now I want to indicate somehow visually the sum, how the sum is working with T here. Like I'd like to somehow animate it. Make a dot move along that line. In fact, I can add a dot, right? And I can move that dot, or I can keep adding dots. Almost perfect. Now you see we've generated that same line, and it's using a unit vector, and that's why it was easy to guess these things. So it's this plus some amount in the direction of that unit vector, which it doesn't matter which way it goes. Now, how do we make something move along there? Well, now it's been a couple hours since what you just saw, wherein there was a lot of trial and a lot of error, mostly error, and a lot of trying to demonstrate the simple and singularly most important fact about this parametric form. And the neighbor has just started with the power drill, so hopefully I can get this done quickly. I found a very cheap and easy way to I don't even need to do any of this to demonstrate what's going on with that graph. Now what I've done is I made a copy of that line right here after creating it. I think this is the same as the original one. And then I start a timer. This is now set for once every 1/10 of a second. And I have my own position, double parameter, static variable, and my static pointer to the same function. And I work out how to map the value returned from that position thing into client coordinates so that I can set the cursor position at the point where the point would be plotted for this particular value. And we'll have to be decrementing it by 1 every timer. And now recall the function, how it works. It's vector plus t times unit vector. Okay. So if t increases by an amount 1, and the length of this thing is 1, then the distance that the point should move will be 1. That is, an increase or decrease of 1 in this value, it causes an increase or decrease, or whatever, right? A directional increase or whatever you want, change in the position of the point, a distance 1. So these are the velocity, if you like, of the point is given by the rate of change of this variable per unit time, and now in this case it's 1 every 10th of a second, so that should be 10 pixels a second. And what I'm doing is I'm plotting the cursor where it should go, and we should see it moving at 10 pixels a second. And it should be pretty obvious, assuming the timers get through at the rate necessary. I might have to use a slower timer. And 100 milliseconds. Timer has the least priority of all the Windows messages. Okay. Now that to me certainly looks like 10 pixels a second. You can see that it's moving at a rate something like that. What I can do is slow this down. Now it should be 1 pixel a second. So every second I'm adding or subtracting 1 unit of this, and that should correspond to 1 pixel. which may or may not show up as motion because, there's granule. Go. Is it running? Okay, here goes. Quickly. Certainly looks like 1 pixel a second on average. What we could do is quickly, before the noise starts again, do it twice as often, half as much, maybe it'll look smoother. Pretty awful noise, I know. Almost done. Okay. Check. Okay, there's a pause in the noise. It's going to have to do. The noise won't stop. So figure it out. The speed and the in terms of pixels is the same as this parameter that's passed in. And that's an important fact. It'll become of use later when we're dealing with those splines and trying to make them move at constant speed. And you'll see that will be quite easy if we get them into parametric form like this. Anyway, gotta go. Too much noise. See you. Bye.